All right, so what we're looking at here, it corresponds to the Honors Chemistry Practice Final Exam, questions 82 through 84, and that's the same as the CP Final Practice Exam, 85 through 86. And the question starts with, in 85, you have 12 grams of each reactant, and want to know what mass of a product is going to be produced. And then we're going to go through the whole percent yield, limiting reactant, that sort of thing. So we're going to have 12 grams of each reactant. The two reactants we have here are PbNO3, so that's iron 2 nitrate. I'm going to start with that one. Put it over 1. So this is going to be stoichiometry. We want to find out, first thing we want to find out is what's the limiting reactant here. Okay? The limiting reactant, it will tell us, when we find out the limiting reactant, we'll also find the theoretical yield, and that will be the answer to our question 84. What amount of that product are we going to find? Okay? So we're looking specifically in and yours is 82 in honors. 82 in honors, 85 in CP. The mass of sodium nitrate is what we're going to look for. So that's one of the two products we're seeking here. Well, I've got a mass here. The first thing I have to do is convert it into moles. So I'm going to kind of scroll down here. Now, we just looked over what is a limiting reactant. So what we're going to do is go from reactant number 1, the amount of reactant 1, and find the amount of the product sought. And this will tell us then what our theoretical yield is, and also will help us identify what the limiting reactant is. So now what we're doing is taking these definitions and we're doing a practical problem to see how it applies. Okay? So the first thing I want to do then is to find the molar mass of lead nitrate. I'm going to do it down here just a little bit to make room for both of these stoichiometry problems. So we've got lead, nitrogen, and oxygen. Since I'm doing this for an honors class, I'm going to use the honors references. The CP class will have a different set of mass numbers, atomic mass numbers. You just use the numbers from your periodic table. So on the honors periodic table, the mass of lead is 207.2. The mass of nitrogen is 14.01. And the mass of oxygen is 16.00. And we're going to have only one lead here in the formula, so that's times 1. The nitrogen, I've got 2 outside the parentheses, only 1 nitrogen in this nitrate formula. So the 2 is multiplied times the 1. That means I have 2 nitrogens. So using the numbers from the honors chemistry periodic table, that would be 28.02. And in the nitrate formula, you have 3 oxygens times the 2 outside the parentheses means I have 6 oxygens. So 6 times 16. Well, that can't be right, is it? 96. And so I've got 2, 2, 15, 21. Let's see, 11, 12, 13. Wait a minute. Yep, 13, carry 1, 3. 331.22. I've got an empty slot right here. Now, in math classes you've had up to now, you just wrote a 0 there. But in the sciences, writing a 0 there would be kind of lying about the precision of the answer here, and we don't want to do that. We want to be clear about precision and accuracy. So I ask students, instead of putting a 0 there, if they want a placekeeper, put an arrow. What that means is then, because there's an empty slot in this column of digits, this number has to be rounded off. So I'm going to get 331.2 grams of lead 2 nitrate or lead nitrate equals 1 mole of lead nitrate. Okay. Now I have an equality statement. So this number here in front, this is the molar mass for lead nitrate. I ask you always to write this. Now if you take AP Chemistry, you're going to skip that step because all you need is that number. You need to know what goes there. But by practicing this over and over and over again, you will know what it's supposed to be and why we're building this conversion unit here. It's not just plug and chug. You understand why you're doing it, and hopefully it will give you more skills to apply things in ways haven't done before. Now what we want to do is to match the units and species here with what we put on the bottom, and this is the side of the equality statement with matching units and species. So I'm going to put 1.2 grams of lead nitrate. Now if we use IUPAC namings or nomenclature, we call that lead 2 nitrate. But when lead combines with nitrate, it almost always does it in the lead 2 form. And so commonly you're going to find it written, if you order it or find it on a bottle somewhere, it's going to just say lead nitrate. And so the other side of the equality statement goes on the top. Alright, and when we cancel, just in the same way you cancel x's and y's in algebra, we can cancel units of measurement and species, and so we're now where we have moles of lead nitrate. Now that we have moles of our starting amount, we're ready to get it into the moles of the other species we're looking for. And the problem says we're looking for silver nitrate. Let's see, what was it? 82. Yep, sodium nitrate, I'm sorry. So what we're going to need now is a balanced chemical equation. So we got two starting chemicals. We have lead nitrate and we're going to be reacting that with sodium chromate. And the products we're going to get will have, since these are two-part chemicals, they're going to trade places. Okay, the lead's going to go with the chromate, the sodium's going to go with the nitrate. I'll start with the lead going with the chromate. Now chromate has a 2 negative charge, and we said this lead over here was 2 positive. That's why we called it lead 2 a while ago. So that means this is already balanced. And they're putting the sodium with the nitrate. Sodium has a 1 plus charge, and nitrate has a 1 negative charge, and you're supposed to memorize certain polyatomic ions. You should know that one has a 1 negative charge. So that's balanced. What we have to do is balance the equation now. So we have lead, nitrogen, oxygen, sodium, and chromium. I'm going to make a kind of grid here for what we call an atom inventory. Getting off the screen a bit. Go back up here. So I've got right now 1 lead. I've got 2 nitrogens, 3 times 2 or 6 oxygens here, plus this 4. So I've got 10 oxygens. 1 sodium, 1 chromium. Now on the other side, I currently have 1 lead, 1 nitrogen, 3 oxygens here and 4 here, that's 7. Got 1 sodium and 1 chromium. Alright, we want to save oxygen for last. And so the thing that is not balanced right now will be the nitrogen. We're going to start trying to balance that. I have 2 nitrogens on the left with only 1 on the right. So I'll put a coefficient 2 in front of the species containing the nitrogen. Once you have all the formulas balanced, you can't touch the formulas. You leave them alone. Okay? You can only use coefficients in front to multiply the number of those formulas. Okay? So 2 of those is how we're going to get the nitrogens balanced. That's going to change the number of sodiums, the number of nitrogens, and the number of oxygens. What now? Oh, right here? Oh, well there you go. That'll fix that, won't it? Did I misread the problem? Yeah, I did. Okay. So now, we're now going to have 2 sodiums. We're going to have 2 nitrogens. And we have 4 oxygens here, plus 2 times 3 are 6, giving us 10 oxygens. And the equation is balanced because all the number of atoms or the number of atoms on both sides are all equal. So there's our balanced equation. We can use this balanced equation then to build what's called a molar ratio. Alright, now this is not a conversion unit, this is a molar ratio. Conversion units come from an equality statement. A molar ratio comes from a balanced equation. These two things are not going to be equal. We're going to put the matching units and species, that matching what's here with on the bottom here. Well, this lead nitrate can mean one lead nitrate formula unit, or we can say it's moles of all these things. So that's what we're going to do. We're going to say it's 1 mole of lead nitrate on the bottom. And on the top, we're going to have the thing we're looking for, which is sodium nitrate. And now we have 2 sodium nitrates. 2 moles, we can say, of sodium nitrate. We can cancel units of moles and cancel species. And we have moles of sodium nitrate. Now we have to get to the mass of sodium nitrate, so we need another molar mass. On an honors periodic table, sodium's atomic mass is 22.99, nitrogen is 14.01, and oxygen is 16.00. We're going to have one of these and one of these, and looks like 3 of these. 22.99, 14.01, and let's see, this is 001858, is it right? 48? You're right, 48. Okay. So this is 10, and that'll be also 10. And that would be 15 then, and then 8, right? I didn't carry the 1? Am I making a little silly math mistake?
No, I got confused because you didn't put your 1 up there. That's why I said it 15. It's fine.
Okay. Alright, so now we don't have anything to round off here because there are no empty slots. So we can simply say this is grams of sodium nitrate equals 1 mole of sodium nitrate. Okay? Now this time we want the moles to go on the bottom because it's going to match the moles on the top here. So 1 mole of sodium nitrate goes on the bottom, and the other side of the equality statement goes on the top. 85.00 grams of sodium nitrate. Canceling units and species, and now we're ready to do the math. Has somebody already done the math? No? And I can do it. I just wonder if somebody already had it done to save me the time.
170 times 12, or if that's 120, I think it's 12.
Say what? 12 times 2 times 85. Hit enter and then divide by 331.2.
I got 6.15.
That's what I got. 6.15. Oh, I got you. You multiply this times this and then times, I got it. Okay. Underline the insignificant digits. You look at all the measured or calculated numbers in the problem, find the one with the least digits, that's this, and match the, we have 3 digits here, we want 3 significant digits down here. And that's going to give us then 6.16 grams of sodium nitrate. Alright, so there's our first one. Our second one then starts with the other 12 grams of the other reactant, that's sodium chromate down here.
How do you know you have 12 grams?
Because the problem says 12 grams of each, doesn't it? Of each reactant?
Yeah.
Okay. So now we need the molar mass of sodium chromate, and we don't have that yet, so we have to calculate that. Since I've shown you how to do that, I'm just going to crunch it out real quickly, okay, unless you already have it. I got 161.98. Is that what everybody else got? And when you're taking AP Chemistry, that's the way you're going to do it. Okay, you're going to skip all the calculations down here because now you hopefully have built up that pattern in your head of how you do it. And so you're just going to crunch it out in your calculator, and you'll have a calculation that looks like this. Okay, 22.99 is the atomic mass of sodium times 2 plus 52. That's the mass of chromium plus 16 times 4. That's the atomic mass of oxygen times 4.
What's the pattern, like, from chromium, whatever, sodium chromate? How did you know to go there? I don't understand that one.
Because the problem said that we're going to start with 12 grams of each reactant. And in the problem, we have 2 reactants. I have to have the starting mass of both, the starting amounts of both. And the rule is that we're going to find the amount of the product salt. The amount of product we are looking for is sodium nitrate, this stuff right here. And so both times we're going to try to find the mass of sodium nitrate. The smallest amount is going to be our theoretical yield, and it's going to identify what a limiting reactant is. Yes? Mm-hmm. And so we have the same, we're going to use this same molar ratio, or we're going to use the molar ratio from the equation here. So we're going to have, let's see, 1 mole of sodium chromate. Whoop, I don't know why I put that in red. Keep my colors matched up. 1 mole of Na2CrO4. And we're going to have 1 mole of lead nitrate. So we're just using the coefficients of the balanced equation.
What's the secret to lead nitrate?
Oh, I don't know. I want to go to sodium nitrate, don't I? 2 moles of sodium nitrate. That's right. I don't know why I was going to the other one. All right, and then we want to do the mass of sodium nitrate, or the molar mass of sodium nitrate. We already have that. So we're going to put the 1 mole on the bottom to match the units and species here. And then the mass goes on the top. No, that's not right. It's just 1 sodium. Cancel out units. Cancel out species. Do the math. So this is the rounded answer?
Yeah.
Does everybody agree with that? You didn't get that answer? You did get that answer. .6 is what I got. That's after we round it. Now you have to know how to round it, but we're going to just kind of jump through that step right now. And so what we have here is 12.6 grams of sodium nitrate starting with this reactant, but 6.16 grams of sodium nitrate starting with this reactant. So since this is the smaller amount, here, this is the theoretical yield. And that tells us that this species, lead nitrate, not that amount, but that species is the limiting reactant. Okay? Now that we've determined what the theoretical yield is, we're ready to go about calculating a percent yield if it gives us an amount here. Where's that? Okay, if we get 1.3 grams of lead chromate, Oh, I got to do a different product, don't I?
No, the percent yield was 12 grams. No, it's not.
Okay, so now I've got to do a percent yield for a different product. Okay. So number 84, corresponding to number 87 on the CP exam, is actually asking about a different product here. It's asking about this product, not this one. So we really only have to do one calculation because we know what the limiting reactant is. This is the only calculation we have to change right here. All right? So this would be 84 and 87. So we're going to do this same calculation right here up to this point in the calculation. Once you find the limiting reactant, unless you change the amounts of the reactant, the limiting reactant is going to remain the same. And the question says number 84 and 87 say we're starting with 12 grams of both reactants. So all we're going to do is just change the product we're looking for. All right, now we need to look at our balanced equation. Instead of going from this to this, we're now going from this to this. That's a 1-to-1 ratio. So I've got 1 mole of lead nitrate and 1 mole of lead chromate. All right. So we're going to need a molar mass for lead chromate. Well, the question number on your honors practice final exam says that 12 grams of each reactant is mixed together and 1.3 grams of lead chromate, that's this stuff right here, is collected or produced. What's the percent yield? So we're setting it up right here to find out the theoretical yield of lead chromate. We know from our previous calculations that lead nitrate has to be the limiting reactant. So we only have to do one mass-to-mass calculation.
So you start with the limiting reactant?
You have to always start with the limiting reactant. Once you find it, you always start every calculation after that with the limiting reactant. All right, so we can sort of cruise through some of the more complex math. You know how to do this, hopefully. The molar mass calculations we've done. So I want to calculate the mass of lead chromate. And so I'm finding, sure. And I got 323.2 as the molar mass of lead chromate. Is that what you guys got? Sure, meaning you haven't done it, right?
I agree.
Oh, okay. Oop, okay, that's right. And you get 11.7. Now, I didn't go through and cancel everything. That's what you probably should do. And so that's the actual theoretical yield for problem number 84 on the honors practice exam, problem 87 on the CP practice exam. And what we want to do is compare that in a way that gives us a ratio of this theoretical yield to the actual yield. And the actual yield, the problem says that we have 1.35 grams of lead chromate produced. Okay, the actual yield then is 1.35. That's what the problem tells you. That's the actual yield. A percent yield is actual yield on top of theoretical yield times 100. So we're going to take that actual yield, 1.35 grams of lead chromate. We're going to put it over 11.7 grams of lead chromate. The theoretical yield. We're going to multiply the whole thing times 100. Now, something to notice here really quickly is when you're calculating percents, if your units don't cancel, something's wrong. When you're calculating percents, if the units don't cancel, there's something wrong. Now, in that video we saw, there is a case where sometimes they have mass over volume percents, which don't make any sense, as the presenter said. It doesn't make any sense. Okay? Percents should have matching units top and bottom. Okay? If they're not, you need to make sure they do match before you do the math, or at least justify the reason for calculating it that way. Okay? So, and in this case, the units, the species cancels as well. So 135 divided by 11.7, 1.35 divided by 11.7 times 100. And that's what I got, right, 11.5%. And that's 11.5% yield in what? In the lead chromate. Okay? Most of the time when you're doing percent yield calculations, you're going to use the same product when you find the percent or the theoretical yield, and then turn around and use that as the thing you put on the bottom. But you got to read the question, because in this case it asks you about a different product. Make sure you're answering the question that's being asked. Does that make sense? Just be careful. Any more questions about the practice exam?
Can you go to gas wells?
Sure we can.